Welcome everyone to another evening with the Berlin Functional Programming Group. We're going to get started shortly with the talk, but first I'm going to put some links in chat for everyone. You can follow us on Twitter. You can find recordings of previous meetups on YouTube. This meetup is being recorded and will also be posted to YouTube afterward. There is a channel for Berlin on the FP chat Slack group you can check out. If you would like to support this meetup, then you can buy a t-shirt, or new for 2021, I have finally started a Patreon. And if you care to support me on Patreon, I should say support us, but at the moment it is largely me organizing the meetups, although maybe someone else will start a study group again in the future. But I appreciate that if you want to offer the encouragement. Also, if you wouldn't mind, just if you haven't already, please type into the chat where you're from, just so Csaba can see where everybody is joining us from tonight. We usually get a pretty international audience. A lot of people from Berlin, but also people from elsewhere around the world. India, Amsterdam, Germany, Brazil, Canada. We have a global reach. Seattle, very nice. Cool. Russia. Okay, cool. So I am super delighted and excited that Csaba Hruska is joining us this evening to talk about GHCI and modern techniques that might be applicable to the design of the Haskell compiler. This seems to be a topic a lot of people have an interest in, and it sounds like he has a lot to talk about. He's been working on the Grin compiler project for some time, and I think he has his own Patreon, and he can share a link perhaps later, and you should check that out as well. And I hope he talks about some of his work, or you can ask him about it. If you would like to ask a question during the meetup, you can go ahead and ask your question in chat, and I will wait for an opportune moment to interrupt Csaba. And if you want, I will let you unmute and ask your question yourself. And if you can't, I can ask it for you. Just make sure I can pronounce all the words in your question and your name as well. So that's it for me. I'm going to hand it over to Csaba. And Csaba, thank you so much for joining us this evening and agreeing to talk about your fascinating work with the group.
Well, thanks for having me. So let me share the screen. All right. Well, does it work, or what do you see?
Yep, I see. Yep.
The full screen, or just a fraction of it?
Now it's full screen.
Oh, excellent. Because okay.
Looks good.
There's a yellow frame here anyway, so I believe the Zoom does its work. So next-gen Haskell compilation techniques. So first of all, I'd like to talk why am I interested in this thing. So Haskell is my favorite programming language. I'm also interested in compilers, but beside that, I'm interested in low-level programming, like high-performance computing, like 3D graphics. And I used to be a C++ programmer and also like machine code. So I tried to do those high-performance things in Haskell, like writing a 3D game. But I wasn't satisfied with the results, so it wasn't efficient enough. And I just took my interest, like I'm interested in compilers. I started to read papers about Haskell compilation, and not just how GHCI compiles Haskell. I also was interested in other languages, other optimizations, and other Haskell, other lazy language compilation techniques as well. So, and so this is why I started the Grin compiler project, and the vision is to is to take GHCI as a front end, because I have no problem with that part. But this compiler project focuses on the backend part, and I took the Grin IR. The Grin is an intermediate language. It was described and appeared in 1999 in Urban Bookist PhD thesis. It's so it describes the IR and the optimizations expressed in this IR. And I really like the result. It's not STG, it's a different approach. But
what's IR?
Intermediate representation. So it's a different approach. I liked it pretty much, and because it gives opportunity lower level optimizations. STG doesn't focus on that, but we will get to this point. And so that's the optimizer part. It focuses on low level. But for the front end, I started to use GHCI, to work with GHCI 2 years ago. And the purpose was to export the IR of GHCI, and I had to learn the internals, and also had to learn how the runtime system works and what the primitive operations are. So I gained quite a bit of experience with the GHCI internals, and also have tough times with it. So I'm going to tell about this during this talk. And so this talk is not a GHCI Dev 101, but you can ask if you have questions. So, but I mean, it's not a Dev 101, is that I'd like to think more freely about Haskell compilation. It's not, I take GHCI as a design, an approach of Haskell compiler, but I think the other approaches are also important, and also important to be open for alternatives. In my opinion, GHCI reached the local minimum many years ago, and I mean regarding the pipeline architecture, and to to make progress, I believe that this pipeline architecture needs to be changed a little bit, but that's my personal opinion. And also, GHCI has a unique design compared to the mainstream languages, and the bad part is that it makes hard to utilize the results from the mainstream compiler technology. So that's also to me, it's a motivation to just, if it's possible, it would be worth to make closer, to step closer to the mainstream approaches. All right, so GHCI is an old, well, it started 30 years ago, and the technology was absolutely different back then, had different technology constraints. Like the average memory in 1990 was 1 or 4 megabytes memory, and I believe that it shaped the architecture of GHCI and still has effect. I mean that roots has effect on GHCI, and I believe it never was, obviously it never was a goal to make a high performance compiler. The goal was to explore the possibility of pure computations and how it mixes with I/O, and also whether it's possible to add exceptions to Haskell or concurrency and type level programming. And GHCI architecture served this research really well. But again, it never focused on low level optimizations and stuff like that. But that's fine. So today, hardware constraints is absolutely better than it used to be. So memory is abundant, and that's from the compiler perspective. It means that the IR, the whole source code, and the intermediate representation of the program can fit into memory, and complex analysis could be done. And the computation power is also increased a lot. So maybe those constraints that were constraints back then are not anymore. So here's an overview of GHCI pipeline. It compiles the program per module, and in the end it links with the runtime system, has multiple stages, and every stage has its purpose. The right side, the yellow diagram, just shows the complexity of the pipeline. The point is that the logic, architecturally, every stage has its purpose. Like the core language got the main focus in the community. It's typed, and its type system is the system F with coercions, and it's really stays close to Haskell, and everything below core is related to the runtime evaluation of Haskell, but it's not in the focus in the community. And so what I mean is, whenever you want to develop GHC, you have to choose which part you are interested in, because it's impossible to understand every piece, every invariance of the system. So that's the way to go. So in general, the programming languages and compilers could be split in these layers. Like there's the surface language, where the type system research and module system syntax and metaprogramming research is done. That's what the programmer interface with, and it serves the programmer. And the lower level, the IR, optimizer code generator, is for optimization, is for how it runs on the machine. And the interesting thing is that these lower level IRs could have a type system, but the type system has different purpose than the surface language type system. Its purpose is to express the intermediate representations invariants, to catch miscompilations, transformation bugs. So it's a tool for compiler engineers to help their work. And also there's the runtime system with a lot of features. In case of GHC, there is the garbage collector, profiler, threading exceptions, and it's really complex. And anyway, we will see how it's possible to make it, what would be the opportunities to improve the situation. So in this talk, I'm going to focus on the backend part only, because it's really scarce of focus, and it would be important to have more people working on this area. Anyway, I'm interested in this field anyway. So these are my list of properties that are important regarding the compiler backend. So it should be, and also this is according my experience when working with GHC code base. So it would be great if the compiler and the runtime system is easily maintainable, and if the compilation speed is good, that's also a good thing. And should compile efficient code, and the tooling should be, runtime tooling should be useful, and the program should be observable at runtime. And my opinion is that the most important thing is the developer experience, as is is really important, because that's so when you want to add the feature, and you have an idea, and the compiler has gives you bad experience, you just give up, and so that developer experience is needs to be good to attract people and make progress with the project. And it's also important to do efficient engineering. What I mean is, it's useless to redo the normal, to solve the standard problems in our domain. The good way is to do the only which are special, and use the de facto technologies available to solve this problem. And during the decades, new algorithms appeared, and new system programming languages, and new algorithms for static analysis, for compilation, and new system programming languages appeared, and new type systems. So and from the practical perspective, new libraries like LLVM or DSS solving like metaprogramming or other runtime system or tooling related problems appeared, and that wasn't available when when GHCI started. So this could change the way we see Haskell compilation. So using these newer results, the developer experience could be improved by, like, this is what I'm talking about, is the ideal world. It's not you might see it's not feasible in the present, but what I'm describing the point where I think is worth to endeavor, where to reach, where to. So developer experience could be helped if we could be improved when the code validation are automated, like and when reducing code complexity is also really important. The analysis, the compilation time could be faster if better analysis technology would be used, and the compiled program would be faster if better optimizations would be done, and the runtime system, well, it's better when it's simple and maintainable. And my hypothesis is that if GHCI is easier to develop, then more people will develop it, and then the better Haskell will have better user experience. Then it will create more Haskell users that will result more GHCI developers. So I think eventually this can shape the Haskell's future also. All right, so this is kind of wish list what I faced, what I had during working with GHCI. Well, GHCI got a new build system, Hadrian. It's absolutely a step forward. It's a great improvement, but the compilation time is still 40 minutes to me, or definitely more than 30 minutes. And that's not the time when you won't stay in flow for 40 minutes just to see the results of your change. Especially, yeah, you might say you won't need a full recompile, but there are cases when you need it. So anyway, so compilation time was an issue. IR accessibility. Well, unfortunately, GHCI doesn't have serialization for those IRs. What it has, it can serialize some core, but not directly that data structure what defines core. So I needed to write it on my own. And the program observation is still an unsolved problem in Haskell. Like, there is no debugger when you can stop the program and just see what's in the memory. Well, that didn't help. Well, it's important to have well-separated compilation stages, and I mean that for reasoning, it's it's a must to understand what is happened so far, the compilation, what state the program is in, just to, because, but so as I said, I want to think freely about Haskell compilation, and when I playing with silly ideas, how to change deep parts, like big parts of the pipeline, it's if I always have to think about the tiny implementation details of the runtime system, I just couldn't do this kind of thinking. All right, and that also the last one, which is also important, is that it's good to allow the programmer to work on its own language and its own code base, and do not restrict to use GHC code base. The problem is that GHC code base is, I would say, it's not the Haskell experience, application development experience. It has its own custom build system. You cannot just drop in a library as a dependency. You have to choose from a narrow set of base libraries. You cannot just add a new serialization library with all its dependencies. So that's so that was a restriction, and also I think it has effect on experimentation. So what I come up with is to make reasoning easier is I created this external STG intermediate representation, which is a copy of the GHC STG, and I changed the pipeline to export it. In the whole program IR is exported to this full pack file, and then I was allowed to process it independently from GHC code base. Then for simplify to understand the semantics of the Haskell execution, I started to work on interpreter for this external STG, which supports all GHC premobs and the runtime semantics and the necessary parts from the base library. And it doesn't require modification on the library part. It just everything what compiles with the standard GHC just works or should work with this interpreter. And the point is that the interpreter, the interpreter can define the semantics without the implementational detail. So it makes easy to reason about the lazy evaluation and the possibilities of optimization, because it doesn't contain the GHC's implementational details. And so it's like a simplified and less efficient version of program execution environment, but it's much more simpler, and like it sounds like a step back, but for simplicity it's a step forward, and it makes it easy to imagine alternative backends, for example, or alternative analysis or optimization. So all this framework what I build is to allow experimentation of different areas of the pipeline, like the memory management, data representation, vectorization, and handling of laziness. Because I've seen or read very interesting papers with promising results or excellent performance results, which I believe could be applied to compile Haskell, but all of them are different from GHC's take. But there is a lightweight version of authoring the pipeline. It's like so GHC's design decision is to compile Haskell unit Haskell modules independently, one by one. So it doesn't optimize multiple modules together. Well, but yeah, okay, it does with inlining, but it compiles. It doesn't do low-level optimizations with this. So this could be changed if the pipeline would be altered to export the external STG, the STG IR, and then optimize it and transform and feed it back to the GHCI compilation pipeline to generate the executable. So that would be the minimal change of the pipeline to support lower level optimizations. So yeah, is there a question? No? All right. So, but beside this simpler approach, if we want to change the core part of the pipeline, like the lazy evaluation, well, it's possible. So let's see how GHCI does it, and then we will see what's the difference. So GHCI builds the STG machine to do efficient lazy evaluation. And question: why is lazy evaluation problematic? So it is problematic because the control flow is statically unknown, and the optimizer and the code generator needs the control flow information to generate efficient machine code. GHCI does strictness analysis and heavy inlining for optimization, but the key point is its runtime system, which is fine-tuned to handle these indirect jumps, and they put big effort, a lot of effort on this, and it works really well. The bad part is that the standard optimizers like LLVM don't like indirect jumps, and it just kills the optimization capabilities. And the other approach will be the defunctionalization, where the point is to remove the indirect calls and replace it with direct calls. So the good thing is that LLVM loves that, likes that. The bad is that according to published papers, it requires a whole program analysis, which is practically not, so this is not practical, but in my opinion, it's possible to relax this constraint, but that's vaporware. But the idea is to, this is something what I plan to do, but I haven't reached this point yet. Maybe this year I will see, hopefully I will reach, I will do this. And so the idea is to take the whole program IR and split it into chunks and do control flow analysis in the separated clusters, and do defunctionalization for those calls who are proved to stay inside the cluster, and use the STG indirect slower representation of slower version of calling conventions to which for those calls who calls other clusters. So anyway, that's the vague idea. But so the idea is to, so far, according to published papers, it needs whole program optimization, but I believe it is possible to relax this idea. So yeah,
Csaba,
question?
we have a question. Yeah.
All right.
Manuel has a question. Manuel, would you like to unmute?
In your example right now, are code clusters the same as Haskell modules?
Yeah, so code cluster size can be adjusted to arbitrarily. So if you set to Haskell module, then you will get the same optimizations what GHCI can do. So, but what I meant code clusters is you can put arbitrary amount of IR into a single cluster, like a whole full 2 modules, 10, or a full package, or multiple packages. And if this concept work, then the idea would be to set the cluster size so that you get fast, good enough compilation time. And so that's it. Or
Thanks.
Okay. All right, so this is an example what LLVM would do with direct function calls. So the input Haskell program, ideally, so I mean, in theory, the Grin IR on the left describes this Haskell program, which adds up numbers lazily and prints the result. And Grin can remove these indirections and just compile it to a tight loop. And LLVM compiles this into a 2-instruction program. And so this is something what LLVM cannot do when you compile it with GHCI Haskell. Even if you, so I mean, when you're using LLVM backend, it will not result this code. So this is really promising to me. But I want to note that in practice, the complexity of Haskell compilation is not about handling laziness at all. The complexity is in the features of GHCI Haskell, like it has more than 400 primitive operations, and the simpler ones are the array and numeric number arithmetic. The more complex ones are the threading, synchronous, asynchronous exceptions, foreign function interface, and they interact with each other. And so recently, so I'm still writing this STG interpreter, and to extract these primop semantics from the implementation of GHCI runtime. And that's how I eventually learn how it works. And it's so my experience is that the manual the specialization of the special cases in the implementation and a lot of details just hides the high level semantics of these primitive operations. So I believe it's the interpreter will help others also to understand the runtime behavior of Haskell programs. So right, so static analysis is also the other part what I want to change in the that is important in Haskell compilation. Let's see how GHCI works regarding this. So it's it has this multi-purpose analysis, the demand analysis, which at the same time it calculates strictness properties, liveness properties, and unboxing properties. It's specifically created to serve GHCI. It's not a generic framework. Works on core and works on single module IR, and I believe it works on only so analyze top level functions and don't analyze multiple top level functions in the same time. That's because it was designed to be fast enough for practical reasons. It also saves the results into the HI file, so it is used when functions are inline. So that's how GHCI works. But in 2016, the Souffle datalog compiler was released. It's an open source project, and so datalog is a declarative language, and this Souffle compiler was specifically created to write static analysis, and it can compile the declarative description into efficient C++, parallel C++ with memory efficient data structures. So I really like this system. I used it, and I believe it's a more generic and it's also more efficient way to write static analysis. So here's an example. If you're not familiar with Datalog, the syntax is Prolog. It's taken from Prolog. So this example calculates the reachable points of a graph with the inductive rule. So the Datalog describes relations. So the closest languages you can think of SQL, but Datalog can express recursive relations. That's what inductive rule does in the last line. So there are two relations declared: the edge and reachable. And the edge is the input, the output is the reachable, and you have to give the initial facts of edges. And then the two rules in the two last line, you can describe your analysis here, which is the reachable in this case. So either it's a x, y is reachable from x when there is an edge from x to y, or the inductive rule is that from every reachable point, if there is an edge, then the other point of the edge is also reachable. So this is really simple, and I use this system to implement a pointer analysis for Grin, which is needed for defunctionalization. It approximates the control flow, and the way it works is that to analyze the IR, you have to export it to datalog facts. Then the analysis calculates the properties, the results, and the result needs to be read back. Then you can do the transformation. And the cool thing is that multiple analyses could be calculated in parallel. And the good part is they can rely on each other. So you don't have to serialize the execution of analysis. Everything can run at once, and they can then increases the analysis, the speed of analysis, and even the accuracy. Like in case of if you calculate reachability and the points to properties at the same time, you can restrict the points to calculations only to reachable points. So why it's useless to calculate properties of a dead variable on an unreachable variable. So it speeds up the analysis. And in fact, it was really fast. Like it analyzed more than 100 STG modules in less than 2 seconds, which is, yeah. So I liked it. You can find the code on the link there. And the other analysis what I was interested in is this pushdown control flow analysis for free, which is a really sophisticated control flow analysis for higher order languages. And this also useful for defunctionalization, and the results could drive the inliner and can tell which functions need to be specialized. So the reason why this algorithm is good, because it's accurate and fast. Accurate, it tracks the connections between the callers and callees, but the key point is that it takes the stack configuration into account. And so it increases the accuracy of the analysis. So this is pretty new algorithm, like 3 years ago was just published. It wasn't used in production yet, as far as I know. So, but I really would like to see how it can perform on real-world Haskell programs. also implemented this algorithm on a toy IR. So regarding memory management, GHCI is kind of traditional, using a tracing GC with generational tracing and generational garbage collector. And the clever idea is that the memory manager is built on a block layer memory API, so which avoids memory fragmentations. So the other, question? All right, so the other novel approach is this counting immutable beans paper, which is using reference counting for doing memory management of functional language. But the idea is to having an analysis to tell which memory cell is reusable. And the follow-up paper, or there's this Perseus system, which was inspired by this original, the counting immutable beans paper. They even made it better. So there's this experimental language called Coco, which implements this Perseus system. And the idea is that it inserts these drop reuse operations in the IR using this analysis. So this is an implementation of the map function, and it analyzed that it can do the update in place because it can reuse the input memory cell. And so I'm interested because this concept works for strict functional languages, and STG and Grin is strict. I mean, strict is that laziness is expressed via data structures, and otherwise the other parts of the language is strict. So this concept could work on those IRs as well. But what is amazing is the performance of this system. So it is compared to OCaml, Haskell, Swift, Java, and C++, and it almost beats all of them. So, wow. So, but again, GHCI compiler architecture pipeline is specialized in a specific way, and without for me, without having this external STG interpreter, I couldn't experiment with these alternative memory management methods. But having a much simplified, slower system, but conceptually much simpler system, I could make experiments with this alternative implementation ideas. And if it works out, then eventually I can create an efficient implementation of the newly crafted, newly designed pipeline. Okay, so the next interesting memory.
Csaba, we have another question from Manuel.
Okay.
So Manuel, go ahead.
Since we sort of have linear types in Haskell, I was wondering whether an analysis like that, whether you can reuse some memory cell is possible if you have linear types, and then if yes, what would be necessary in order to do that? Would you have to compile linear types all the way down to STGs in order to make that work?
Yeah. So well, that's a possibility and a good idea. As far as I know, it's not a high priority. Maybe so it's possible, but linear types were added to Haskell to support API invariants to express but not intended to use by the backend. But definitely it's an option. But the good thing of what I like about these systems is that they don't rely on this information. Eventually, I can imagine imagine that this Perseus and other systems analysis results would be showed on the source code. And if they figure out that some value is linear, you can constrain it in the type system. That would ensure that the memory management analysis will recognize it and use the in-place update. But it's also possible to enforce it, like make it sure that type driven, make the in-place update type driven. That's possible, but that's more reliable, but it's more manual. That's, I would say. So the other thing, which I believe it's amazing, it's eventually it's not possible, it's not ready for production use. This as static as possible memory management is a compile time automatic memory management which requires whole program analysis. It has an efficient implementation called Micromitten for a Rust-like language, and it's also, there's a thesis written about this experiment and results, and the conclusion was it's not ready for production yet, needs more results. But what is interesting in this system, this as ASAP, is that so the original idea was written in a PhD thesis in 2017. So it compares several memory management methods in a single. It puts in different methods in a single map, and the axes are whether the memory management is automatic or manual or done at compile time or runtime. And if you put you can put the standard garbage collector, the reference counting, and the C family manual memory management linear types based like Rust, like memory management system. There is a gap, like the right bottom corner of the map is empty, and that's what as static as possible tries to fill. And even though it's too slow at the moment to make it to use it in production, but what is interesting, what I believe, is its static analysis can reveal the lifetime of data at compile time. And this is, if that would be shown to programmers, that that's useful information. But in case of Haskell, that would help you to restrict some types to make linear or whatever. So can help the programmer to understand the software architecture and give insights. So that's what I think. So another field is data representation. Well, GHCI has a uniform representation for values. It stores everything on heap. Everything is represented uniformly. Everything is boxed and has a tag, and it's called. There's the metadata, which is in the info table. Here is two examples how it looks like. Maybe you are familiar with this representation. So, and the thing is that if you have a complex data structure, there might be a lot of indirections, a lot of pointers. And modern CPUs don't like this. So, so the question is, is there any other opportunity? Is there an option? And according to recent research, there is this Gibbon experimental compiler which transforms functional programs into operating on serialized data. That means without pointers or indirections. And later they added a formal system called location calculus and improved their implementation to use it. And the cool thing about location calculus is that its type system ensures that the transformation, like the compiler transforms the full high-level functional programming to operate on this serialized data. So the location calculus type system ensures the correctness of the transformation. And also local allows the two extremes of the representation. It can express the fully serialized, like without pointers, of data representation, and also can express the fully pointer-based representation and anything between. So that's excellent, because that means to me that the compiler can choose the representation of the data structure, and it's not the programmer's task to write the program accordingly. So here you can see in the diagram the two examples what a tree look like if it's represented with pointers, and how it is represented if it's in this serialized way. So it's called serialized because for example, when you store this recorded data structure in file, you don't save the pointers. You serialize the data structure through a traversal, and that's exactly what this does. So here is an example of what does this mean. So there's the tree data structure which stores ints, and the function which adds the values of leaves together. And the serialized representation of the tree is just a buffer, like you can see here. And so the traversal is just pointer dereference, and the case distinction is done through the tag reading, and that's it. So, and the pointer advances. And the good thing is that the CPUs love this serialized representation, because it's cache efficient, and that's what really matters in the current CPUs. And the benchmark results is amazingly good. So this benchmark is about finding a word in a JSON, in a big JSON, large JSON, and it compares this location calculus-based Gibbon version against GHCI's compact normal form, which is the compact region, and the Captain Proto, which is an efficient C++ data interchange format and library. And the Gibbon version of the data representation is tiny. It's less than 300 megabytes, where the Captain Proto needs more than 700 megabytes, and the GHC's compact normal form is more than 2 gigabytes. So, but the other thing which is also amazing is the speed of the system. Like the upper diagram is relative to this location calculus based Gibbon implementation, and it is the fastest, and all the others are much slower than it is. So it would be really interesting to check how would Haskell perform if it would use this kind of representation. So this is so tempting to try. So definitely it's too promising and needs to be tried. And that's my goal with my system, like my STG interpreter framework and the Grin compiler project. The other interesting thing is vectorization, which GHC doesn't have such a thing. It doesn't do vectorization, but there was a project called in the Interlabs research did a experiment. It's called the Haskell Research Compiler. They use GHC as a front end, and they build their own optimizer backend just to check how would the purely functional programming languages perform on numerical computation, whether they are optimizable or good for optimization or not. So they backend specialize data representation and also deals with laziness, like tracks function pointers, try to figure out the control flow and remove indirect calls, replace with direct calls. It doesn't require whole program compilation, and it does simd vectorization automatically. Like it doesn't, the programmer doesn't need to annotate the source code. And the Haskell examples are high level. So they used REPA library to express these numerical computations. Also, although they slightly modify the array built GHC's array primitive operations, but that's it doesn't count because it's not the source program that need to be annotated. And it seems that vectorization makes Haskell suitable for high performance computing. Well, let's see. First, the architecture of this system. So they used GHC as a front end, and the main optimizations are not done in HRC, but they are like the vectorization and everything, the memory representation are done in FLRC on using this mill intermediate representation. And then it compiles to C with intrinsics. So it was open source a few years ago, and I read the source code, and sometimes I was interested whether they do something that is not possible with Grin, but I haven't found such a thing. So it's everything what this compiler did is possible with the Grin IR as well. So the drawback of their system is that the runtime system is not specialized to handle laziness efficiently. So they lose on some generic Haskell laziness dominant benchmark programs, but can win on others. It's like if we check only the computational heavy benchmarks, this HRC Haskell competes with optimized and vectorized C. So there is a paper called Measuring the Haskell Gap, which tells the full detail. So the thing is that it's there is the simd vectorized Haskell with high-level Haskell algorithms, like the idiomatic Haskell, I would say. It can compete with vectorized C. This is amazing. And the interesting part is that even with this computational heavy benchmark, HRC beats GHC, even with LLVM. So that means that probably this system only weakness is the not well-tuned runtime system. That's my hypothesis. All right, so this thing is not related to Haskell, but it's related to vectorization. ISPC is the Intel's SPMD compiler, is a variant of C language with specific language extensions to describe this single program multiple data programming model. So SPMD is mainly done in GPU. That's it requires a language extension where the variables are annotated whether they are uniform and varying. So what does it mean? So GPUs and CPUs also have same instructions, vector instructions, and the expressions, the variables are annotated whether they are constant in all the vector lanes or they are vary in vector lanes. And this is enough information for the compiler to vectorize throughout multiple function calls. So that's a control flow level vectorization. It's much more efficient than a simple loop vectorization. So, and it gives massive speed up, like this one, 6 times or yeah, from 3 to 8 times, right? That's amazing. So I would wonder, would it work for Haskell as well? Like defunctionalization can represent laziness as data, and local can remove indirections from pointers. So would it vectorize as well? So this is really interesting question. Like definitely would worth to check. Okay. So the other things what I want to cover is runtime system and tooling. GHCI runtime system is mainly written in C, but some complex primitive operations are directly written in C++, like exception handling. And RTS has several subsystems, the GC, thread scheduler, IO manager. Unfortunately, the runtime system contains code which are GHCI specific only, like the linker and the bytecode interpreter. But that's how it is at the moment. And RTS also depends on the base library, like it refers some data types, like exception data types, and uses some functions. And the thing, so GHCI RTS does its job, it handles laziness efficiently. The problem is when you want to change, when you want to write some extra code or even understand or just alter it. So as a developer, you will face a big complexity. It uses special conventions, C++ macros heavily for runtime system, heap object manipulation. It's almost like a mini operating system with seed structures with complex invariants. And the problem is that the developer must maintain these complex invariants manually. And the C-type system is too weak to help the programmer. And my hypothesis is that this complexity scares away developers. And I also think that it's practically impossible to make architectural changes, even for experts, because so I have memories when I wrote a complex software in C++, then I changed things, then it didn't work, and it was a long debugging session to figure out what went wrong. And this experience just teach me to not to do extreme changes. And when I switched to Haskell, the type checker helped me a lot, pointed out where to change my code, where to fix it. So I become more ambitious regarding refactoring or architectural changes. And in case of GHCI runtime system, it's written in C, so it's eventually the developer will learn that it is impossible to change because manually it's impossible to, or too expensive or too complex to maintain this invariance. So, but in an ideal world, the goal would be to allow fearless refactoring, and so a sophisticated type system could support system programming, like to write a runtime system in an advanced language, where the type system is capable to express complex invariants. And there are such languages nowadays. Like Rust is a mainstream language compared to ATS, but it's much better than C. Has weaker type system, yes. But my favorite is ATS, is called Applied Type System. And it's a niche language, but really powerful. It's a dependently typed language specifically created for system programming, and it does compile type and proof erasure, so there is no runtime overhead, and compiles to C and has zero overhead interop with C, and it's up to the programmer how he models the invariance of the application domain. So if I would write a runtime system, I definitely wouldn't choose C, rather choose Rust or ATS to do that. And I've seen papers and also watched presentations about this language, and embedded system programmers use it. And also some device drivers were written in ATS. So, but the good thing is that because the C interop is so effortless, it is possible to write only some pieces of the project into this language. So the syntax is derived from ML. It's not excellent, and neither the error messages are, but the features are pretty powerful. So to get back GHCI runtime system, I would rather accept horrible error messages and complex proofs than random segmentation false after I modify the RTS. So I see bigger value to learn a sophisticated programming method than battling complexity time to time. All right, so the last thing is the tools, which are also important, like telemetry, profiler, debugger, visualization, and in my opinion, web technology is the most accessible. That wouldn't mean that we should stream the whole heap to the browser. Don't get me wrong. What I mean is that with this technology, it's if the programmer resource is scarce, like that's the case in Haskell community. So it's better to use whatever technology is already there, and definitely there is a lot of documentation on how to use charting libraries, stuff like that. So I have no problem with this, because with this documentation abundance and technology abundance, I could easily create a visualization what I need quickly. So this is a screenshot of a program that I created. It's visualize the event log from GHCI, what GHCI runtime system creates, and also utilized the modified GHCI what I did. So it can show the call stacks, the call center stacks on the Haskell source code. It doesn't just tells which line and which file is involved. It also gets the source code from the file. So here's a video of them. And so it's definitely much better than printing into your terminal. That's my opinion. All right, JavaScript is definitely not my favorite. But I accept the situation that this is the the cheapest way to create tools, and the tool has a good user experience, and that's the important thing. It's not. I definitely wouldn't write a complex software using this, but this is a thin client which purpose is to do only the visualization, and it works. So for modern tooling, I think this is a good choice. Much better than well, not much, but better. I believe it's better than a native application. And that was it. So the conclusion is it's important to allow to do experimentation easy and to make experimentation easy and fun. It's yeah. Right. So any questions?
So thank you so much for that tour de force talk. If people have final questions, go ahead and type them into chat. It would be great to get a few. And if you can share I was going to ask if you can share the links, but there are a lot of links. Maybe you can share the link to the slides. And then,
Absolutely.
Yeah, I'll put that in you can just send that to me later. And yeah, well, you can put it in chat now as well.
I can.
Yeah, and I'll put it on the Meetup. I'm curious to know what your ambitions are for the project. Are you looking to offer an alternative to GHC? Are you also looking for collaborators to help you build it?
So I don't. Yeah, good question. So I don't want to. In the long term, I don't want to be an alternative to GHC. In the long term, I want to cooperate with GHC developers and make the change GHC pipeline. Like if GHC pipeline would allow to export this IR, like I can create a merge request later on when it's stabilized. So then it would be just a natural option to choose a different backend to compile our Haskell project. And regarding the programming help, yeah, definitely that's a help is always good, but the obstacle is that it needs a lot of reading, like PhD theses and stuff like papers, because a lot of different fields are involved. So this is I'm through this reading already and have a vision, but the next, I think the next stage where it would be possible to connect is when I will be ready with this external STG interpreter, because that would allow everyone to experiment with how Haskell programs are evaluated. Like if they would use my system to export this external STG IR, then they would run running on this interpreter and can learn how different parts of the system works. So it's not about optimization, it's not about memory management, it's just about what does it mean to execute Haskell programs, because that's also something what needs to be learned if you want to write a compiler for Haskell. So maybe if when I finish it, like hopefully it will happen in months, like this year.
You're expecting to finish the project this year?
No. This external STG interpreter.
I see. Okay.
And so definitely the memory management vectorization stuff is a long-term goal, but it's an important milestone to to have this interpreter because it defines the semantics. Like if that would make me sure that everything, I handled every use case, every corner case, every primitive operation. So from that point, I just won't worry at all about the higher parts of the compilation pipeline. Okay.
I think Alex has a question. If Alex, you'd like to unmute, you can ask yourself.
Yeah, I just was curious whether there are other programming languages that can target the same compiler, the same pipeline. I heard Unison is looking for some advanced compiler techniques to optimize their runtime.
But like, is the question that whether the runtime could be optimized with the language, or?
I mean, other languages. Can other languages target the same runtime of the same compiler?
Yeah. So, so it's also what I'm building is what I want to build is a generic optimizer for functional languages, and indeed, an interest front end is work in progress. A friend of mine working on this. So it's and the other interesting aspect is that because my modified GHC supports exporting and importing of this external STG, it is possible to use GHC runtime system for other language frontends. Like Idris could run on GHC runtime and interop with Haskell on the same runtime using same GC, same memory representation. So that's the API is ready for that.
I have a soft question about GHCI. So you only spoke briefly about GHCI, but so I notice whenever I do something with some performance sensitive code, then of course if you would run it in GHCI, it's much slower because it's interpreted. And I'm wondering whether whether you have any insights on whether something can be improved there, or whether that is just going to be as slow as it is and will probably never improve.
So I don't know, GHCI is can use the compiled code, can import the compiled code, but when you I don't know when it loads the bytecode and when it probably the compiled libraries are imported as a compiled code, and the local project is bytecode interpreted. I'm not sure about the details, but so whenever I read GHC's code, I just want to understand how it works, but I'm looking through the perspective of my goals. I'm not learning GHC to follow its track, like follow the GHC design. I'm learning to understand how I could apply different designs. So that's why I never thought how the GHCI could be made faster. But probably if it's slow, then it's because that code what you're running, the computation heavy part is run on the bytecode interpreter, but all the libraries that it refers and imports, I'm sure that it's using the compiled version of the code, because that's how GHCI is designed to. It mixes bytecode interpretation and native execution. But yeah. So I have plans though to experiment with backends using, but I want to use the external STG representation for that. I wouldn't implement a new bytecode interpreter, but I would rather try to experiment with targeting Luajit or something. And maybe that could be faster than the GHCI's bytecode interpreter, but that's just an idea. So anyway, I think that with this STG interpreter, I can reach a milestone when it will be simple to understand how the evolution of Haskell programs, and it would make easy for everyone, like even me, to just to think how to create new backends, like crazy ideas. That will be the point when it will be fun to do this kind of experiments without the hassle of GHC code base, because this external STG tooling is just a regular Haskell library. You can use Stack and Cabal or Nix, whatever standard development pipeline. All right.
Thank you, Manuel, for all the questions tonight, actually. And we have a question from Benjamin. Benjamin, can you unmute to ask your question?
Hi. Did I see that correctly that Grin still emits LLVM and uses it for code generation? And do you think there are any limitations because LLVM is geared more towards C-like languages and doesn't support some of things Haskell would like to have?
So maybe I didn't get the question.
Did I see it correctly that Grin uses LLVM for machine code generation?
Yes, that's correct. Yeah.
And I think there, at least with the current GHC state, there are some limitations that LLVM has, like GHC likes to create tables in code, and it.
Yes, that's so. I believe that's the case. Like LLVM generates. GHC generates C++ and C- from C++ is so C++ is then compiled to LLVM, but the STG machine is expressed in C++ with all the heap object manipulation, and that's what gives LLVM capabilities for optimizations, because there's still so it doesn't understand the invariance of STG machines, heap objects, its structures, and so on, and that blocks LLVM, and Grin doesn't. So the goal of Grin is be direct, like don't do obscure memory modifications. Compile everything into. I mean, that's the goal. If it's not the case, then that need to be changed. But definitely, that's the way that we should focus on. Like that need to be focused to compile such a code that LLVM can understand, and that means that indirect jumps are bad, and random memory operations, heap operations, are also not good.
So I have one more question. I always seem to ask some kind of human question. I'm curious about how people end up doing functional programming, because you mentioned before that you were a C++ developer for some time. How did you end up making this transition from C++ to Haskell and then working directly on the compiler?
Okay, well, so since my believe from childhood, I was interested in compilers. Like at first it was basic interpreters and machine code, but then I just read books about compilers. So it was, even when I was C++ compiler, I checked LLVM, read about LLVM, and I got to Haskell because so at uni there was a class, just a optional one, that was about embedded functional programming or something, and that just sounded weirdly enough to to take it, and that introduced me to Haskell, and I really like the language properties that I seen Haskell from a compiler engineering perspective. Like purity is good because I can do optimization, and that's why I got to Haskell. Then it was just a good experience. Like the type inference is amazing, and also helps a lot. So I seen the opportunity. It wasn't the performance. Maybe even when it was bad, I've seen the opportunity. Maybe in the future, or in theory, it is possible to make it faster. So maybe this kind of view was confusing for some of my colleagues when I was working at like an application developer for mobiles. Like when I said so many good things about Haskell, and they just didn't see the same thing, because I seen the future opportunity, what this language can become. But it's not, maybe it's not the case now. But anyway, I still see it like this.
And was it your own frustrations working with the compiler that made you want to optimize it, or you just can't help tinkering on compilers?
I'm interested in compilers, and the only frustration was to me when GHCI codebase didn't allow me to do the fun experiments. So I expect from a compiler to allow me to export the IR, to analyze it, to give the machinery to save the data, and Haskell is that's one of the strengths of Haskell. You can just derive a generic or show instance or whatever from any data structure, what you in your application, you just print it or save it. It's not the case in GHCI internals, and that was a horrible feeling. That was funny because C++ doesn't have these cool features. Haskell does it, but and got used to it. But when I worked with GHCI codebase, I eventually felt like the same. It was the same times when I was C++ programmer, that I'm so restricted, too many constraints was there, and so that's why I realized that I had to come up with a solution, and this external STG, as external IR, seemed to be the best option to me.
And you didn't say much, I don't think, about the practical goals, but in the talk description, there's mention of making Haskell more useful for industrial applications. And is this is something that you have your eye on?
Yes, I'm all right. So runtime tooling could help the most. That's my I believe. Like if there would be a profiler with good user experience, or a debugger which can show the source of the memory leak on the source code, and stuff like that. That's not exist for GHCI now, but I'm planning to build such a thing for my interpreter. Like I said, the interpreter is much simpler than the actual specialized GHCI runtime system, and I can work in Haskell to add this or experiment with this kind of feature. okay, the execution, the interpreter is much slower than the native runtime system, but it's not obvious how to implement such a debugger or profiler or a space leak analysis. But now I have the power to work on convenient Haskell, and the type system helps me to refactor my application and stuff like that. So I can find the right direction much quickly than I could do when I do it in the native way. So eventually, so runtime tooling could help the most for industrial application. That's the short answer. The other is if Haskell would be faster or could deliver more predictable performance, then people would like it much more. Like there, maybe it could be applicable on high performance areas, high performance computing areas. And that's something not possible today.
What are you thinking about when you say high performance computing?
Like data processing, or like numeric computations, computer graphics. Yeah. So those areas is the one where the C++ is the dominant.
So this is very ambitious. The idea that Haskell could one day supplant a language like C++. I think it's a pretty noble goal, though.
Yeah, I agree. So this is this absolutely sounds overly ambitious, but so it's confusing to see these papers, what the benchmarks from this local paper and the Intel Haskell research compiler, and they perform so well. And the confusion is that why doesn't which I couldn't answer, why doesn't GHC have these features? And the only answer what I could come up with is cultural reasons. It never was on focus. That's my answer.
I mean, it definitely wasn't geared toward industrial applications.
Yeah.
Well, we don't have any further questions, and I think this was really fascinating, Csaba, and thank you for sharing your work with us. So I'll get the link from you at some point and post that. And I think I forgot to ask, where are you joining us from tonight?
Oh, I'm living in Slovakia nowadays.
Oh, Slovakia. Okay, so not very far from Berlin.
No.
Okay, well, thank you for joining us virtually at our meetup, and I hope our paths cross again sometime. And thank you to everyone for your questions and for participating tonight.
Okay.
Thanks a lot.
Okay, goodbye. Take care, everyone. Ciao.
Bye.